Okay, hello again. Okay, we're continuing with our revisiting of root finding, but establishing more rigorous results, and particularly the one thing I hope you're beginning to get is a way of quantifying the rate of convergence of these these methods we're looking at. We're going to look at three altogether. We've looked at two, so we've looked at fixed point, and then we've looked at bisection. We've established that we can call them linear rates of convergence, and the rate of convergence of the fixed point is controlled by the gradient of g, this g function, and in that sense we can compare the rate of convergence of the two. So finally we're going to look at our old friend Newton-Raphson that you may have even come across at A level, but we want to say, well, is Newton-Raphson faster than bisection typically? And if so, why? Not just empirically by just running the two together and seeing that, but we can actually prove that. So that's where we want to get to in the next couple of sessions, or that's 2 or 3 sessions, and that's where one that's in the main material of the roots. So root section is the shortest part of this module, but I thought it's always very helpful to revisit something you've done before in a new way, rather than diving straight into matrix theory, which we do later, which will be completely new. Okay, just a one comment on the fixed point before we move on to Newton-Raphson. So let me just go to the board a minute. There we go, and go like that, and so we know that fixed point method converges for the modulus of the gradient. You can put the subscript n or subscript n minus 1 if you want. I'm just going to leave it off this time. Modulus of g is less than 1, and the key thing, so we've been focusing on the value of g prime, but it's key is the modulus. So that means there's 2 scenarios potentially where this is true, if you like. We've had one, and it gives you a cobweb. So let me draw that. I'm just going to try and draw 2 things on this diagram. So let me use red. So red that's y equals x. So I'm going to draw exactly the same diagram on the right here. Let's go back to color. Okay. That's y equals x, and in the diagrams we're looking at like this, we would plot g of x like this, and the gradient is less than 1, so it will cobweb into the solution. Yeah, subsequent nice beautiful cobweb. But of course it's the modulus of g prime that's got to be less than 1, and this is case where the gradient is negative. So what's the other case? Well, the other case is when g is positive. So g prime is positive rather, and it's like this. That's still also g prime is greater than 1. But in this case it doesn't cobweb, and that's one thing to remember. I think some people sort of pick up on this idea of cobweb and expecting it to do this sort of spiraling in all the time. In fact, in this case it does, it sort of just gets narrower and narrower. You can see what I was thinking. Okay. I tell you what, I'm gonna undo that and see if I can draw that a little bit clearer. In fact, use a slightly thinner ink. So it goes up like that, along like that, up like that. I don't know if there's a name for this. It's like a staircase. Okay, that's a cobweb, and the right is a staircase, and it's because g prime is less than 1. So that still converges, but it converges in a sort of on the diagram of x and y it converges in a completely different way. So I just want to note that those two cases. Okay, and I've got a note to include those in my lecture notes eventually, probably not this year, but you know, you can add that extra case into your notes if you like, and sort of complete the picture. So, all right. So, and that pretty much finishes all I want to say about fixed point for the time being. The thing to remember is it's a linear convergence and it depends on G prime. So now what about if we now return, so if I go back to clear the board, do that, go there, oh no, there, here I am. Right, I've got a few slides here to my right. See if I can make those a little bit bigger for you. There we go. Okay. So the Newton-Raphson method. So the Newton-Raphson method depends on the constructing the tangent to the function you're trying to find the root of, and using that tangent to get to the root. So if you start at xn, you construct the tangent and then go down to the y0 axis and you get xn plus 1. So it's a completely different way of doing things, and intuitively it seems that it might be faster, but it also intuitively it might seem that it's dependent on this gradient thing behaving well. So that's what we want to fold into what we're looking for when we look at the proof of this convergence rate. But that's the essential method, and that's the diagram we want to use. Okay. Okay, so let me then just rederive Newton-Raphson. You know, for most of you it should be familiar, but then we're on familiar ground, and then we'll look at the convergence rate, which I'm pretty sure you won't have come across before. You know, so again, in the same spirit of starting in the familiar and then moving on to the unfamiliar this year, you know, getting a sort of, you know, I'm not really trying to fill your heads with lots of different root finding methods, like go and find a more advanced, more radical, differently version of bisection. I want to actually establish understanding of how numerics work, you know, convergence rates and convergence conditions. You know, that these are the things I really am about in this module. Okay, so hence no apologies for revisiting things we've done before. Okay, so let's go back to the board. Okay. We're on, oh, that's a bit big, isn't it? Still a bit, sorry. Better. So Newton-Raphson. Let me just draw that diagram for our purposes. We have x of n, xn plus 1, and then we have our root in there. Let me draw the function like so. Okay. And the whole idea then is reconstruct the, oops. Construct the tangent at xn, and then it meets at xn plus 1. Right. That's the tangent. So we can then, just by looking at the geometry of this problem, is write down the gradient. So our f prime, the gradient xn, is simply the gradient of this line here. And this is the value of f of x of n. And that's simply minus, it's a negative gradient, f of x of n, which is the vertical, divided by the difference, which is xn plus 1 minus x of n. And then we rearrange that formula to give xn plus 1 in terms of xn. So we have xn plus 1 equals x of n minus f of x on f prime of x of n. Okay, and then we do that for all our values, n is 1, 2, whatever, and we iterate to convergence. And it's a very useful way of finding the root. And in fact, oh, there should be an H on there, Newton-Raphson. In fact, there's a whole bunch of Newton methods, and the Raphson often is often dropped, that extend to multiple dimensions. In fact, one of them we're going to look at in time, if not today, this is worth bearing around it. It's actually this method of using the gradient to find your solution, to iterate your solution, is a very powerful and very useful method. It far extends beyond your simple Newton-Raphson. But what you see is there is also a potential warning here, as we have 1 over f prime in this method, and there's a tutorial example that we'll go through where this becomes worse. So if f prime becomes very small for whatever reason, it goes 0, this method might not work. Well, it won't work. Okay, so we can already see that it's dependent on f prime, but it might be quite quick if it's dependent on f prime. Okay. So what we want to do now, and start to at the end of the session, is establish. Really, this question is what is the rate of convergence? We've encountered 2 methods so far that have linear convergence. And what's Newton-Raphson? Is it still linear convergence? What is it rated? And that's the new thing I want us to analyze before. Okay, so you might be empirically compare Newton-Raphson to others by just running them for the same number of steps. But here I want to show you how you can use the result we've got before. In fact, we're going to use the result from the fixed point method. Cleverly, it is. It's not to do the proof. So convergence now. Analysis of, I'm going to call it NR for Newton-Raphson. Okay, now we're familiar with it. So again, we define the error for a particular problem. So we start with error n plus 1. Okay, we're looking for a rule that gives e at n plus 1 to the error next, and obviously it's never written in that form. We have to do some manipulation and some tricks. And error n plus 1 is just xn plus 1, yeah, the numerical solution xn plus 1, minus the true solution x star. And then we can, but we do know what xn plus 1 is, yeah? That's our Newton-Raphson formula. So we then just substitute in our Newton-Raphson formula for xn plus 1. So that implies then your error n plus 1 equals xn minus f of x of n on f prime x of n, I'll use some Raster formula, minus x star. And actually I'm going to do a little subtle movement. I'm going to move the minus x star bit here, the other side of f over f prime, because it's useful. So minus x star minus f of x n on f prime of x of n. And what do we have here? And this is where, if we were in a physical audience, it would be helpful, because I could just ask the question and someone could answer. So what is this? I'm going to maybe try and simulate asking a question. Is have a little think about what xn minus x star is now in this problem. I'll just stop for a couple of minutes. No, not a couple of minutes, is it? That's right, you all got it right. I'm assuming you've all got it right, which is that this is simply e to the n, yeah? Just got the edge of my video domain there. That's e to the n. I'll do that for the next step. So I'll rewrite that there. So this is e to the n now. So we're starting to get towards an error law. It's not exactly the form that I gave you at the beginning with, you know, e to the power of q times a, but we're getting somewhere when we got it in terms of error. So let's just rewrite that out again. So you have e to the n plus 1 now equals e to the n minus f of x of n on f prime of x of n. So we're going to still have to deal with this term, but at least we're starting to get it in terms of error. Okay. Right. Okay. So there's a few more steps. This is probably the most involved convergence law, but we bear with it. We're getting useful. So now we basically have to try and manipulate this into some proportionality to e to the power or something. So how do we do that? Well, we're going to use our Taylor series. So use Taylor series. And what we're going to do is expand our numerical solution x and n about the root x star. So what we're going to do is we're going to approximate the value of f at point x star by deviating from f of x of n. Seems at this point it might seem a slightly unusual thing to do, but once we get further down the line, you realise that once we get the idea is that we want to get Taylor series with f of x and f prime of x of n, and Taylor series contain your derivatives, right? So and it turns out it's expanding against this. So basically, we're going to try and find the value of f of x star starting from x of n. So your if you like, you've got say x star here, where it's meeting the y-axis, and you're starting from xn, say there. So you've got f of x of n. So you're basically saying, if I started at xn, so a better way of saying it is, you could say, if you started at xn, what is the value of f of x star? Yeah. So, but we know the value of f of x star is by definition is 0. Okay. But we also know the Taylor expansion. So if we start with f of x of n, and we extrapolate using Taylor, or then we get the difference between x star and xn, f prime of f of xn, and then we get the next bit, which is x star minus xn squared on 2 f double prime of x of n, x of n. I'm just going to do it like this at the minute, and then I'm going to introduce some other trick that's very useful here. But this would be your Taylor series, and we can see where we're going with this is that we're getting terms of, again, that look like error, x star minus xn. That's kind of your error n, yeah, or that's minus etn, that term there. That's error squared, right? So that's great. So we can convert this second term into something that is proportional to error, times it with a power. And we've also got our f's and f primes in here, and also a residual term. So that's really cool as well. So the Taylor series is very useful. Now, I told you right at the beginning that Taylor series is useful, and you might think that Taylor series is just a simple extrapolation of function. It's actually profoundly underlying all numerical methods, and as you go on, you'll sort of realize this, that it's an incredibly useful tool. So it's worth bearing in mind. So there's the final trick is, you may have come across in analysis, but we're just going to use it as given with the Taylor series. So let's just write where we're at. So we now have f of x star, if I can write it in a single line, 0. And in fact, I realized that I've run out of time for this video, so I'm going to restart this in the next one, not to make this video too long for you. Okay, so let me just go back to me. Okay, and I'm just going to sign off. So we started to look at the convergence rate for Newton-Raphson, and we're starting to get an equation of e to the n plus 1 to the e to the n, and next time we're going to use some more tools to get it in that form. So it's quite a long derivation, and it's understandable that it will go over more than one video. Okay, so see you next time. Cheers.